Welcome to Tech Fest. This morning we've got Greg Abernathy, and he's going to be talking to us about lightning protection and grounding.
Let's see here. Does this one work? Okay.
Yeah.
All right. Thank you for allowing me to come here and speak on lightning and grounding. My name is Greg Abernathy. I'm an electromagnetic compatibility design engineer. I work in this field doing lightning, EMI, EMP, ESD, all those three-letter words. And I like to have my presentations open. That's why we have the lights up. So if you have any questions during the talk or anything you'd like to add to it, please feel free. We'll just go from there. I'd like to be more of a go along as a question and answer than it is me just sitting here talking and taking questions. I feel like everybody gets more out of it. Lightning, beautiful stuff. What we're going to be talking about is how lightning is generated, how it occurs, what the bright channel, let's see, what this bright channel through here is, versus what these smaller channels or leader formation is called about, and try to dispel some of the myths about lightning. Now, when an object is struck by lightning, such as an aircraft in flight, you notice here that we have we'll call this up front here an entry point, and this an exit point. You notice we have leader formation coming off of a lot of sharp edges. And we'll talk about why this is more faint than what you see in the main channel here. And as you see, the current will flow through the skin of the aircraft if it's a metal aircraft. If it's a carbon composite aircraft, there's other methods you have to do it because the impedance of the skin is too high for it to all the currents to flow on the outside. But the main protection for metal aircraft is to try to keep all the currents distributed onto the skin of the aircraft on the outside of it. You can get struck in flight. Matter of fact, this is when most aircraft are struck is in flight, probably right around the 10,000 foot level, right before the cloud deck, either when they're ascending up or they're descending down is when that usually strikes. What happens is you get a voltage potential set up because between a pocket of energy up in the cloud and the opposite charge, because opposites attract, builds up in the earth below it. And it's like a capacitor. And what's happening is the winds are causing the stripping of the electrons coming off, and all the electrons are forming as a bundle up in the cloud. And as I said, the opposite charge is on the ground. And it'll build up to a point where the dielectric strength of the earth, the ability of the earth to hold those charges away from each other, can't do it anymore. So it breaks down. And that's what this is a breakdown of the charge, of the dielectric between the two points. This picture here, you have there on the ground. It just so happens that it happened to attach at the highest point at the end of the tail end of the aircraft and exited down here at the tug. This can be a very dangerous situation, especially if people are in the process of backing this aircraft up or all. The same phenomenon is going to happen with houses and all this as we go through this. And the discussion right here is we're going to talk about our concepts and issues and things you can do to ask Mother Nature not to take the path through your radio equipment or through your house. Some basic facts. Each second there's about 50 to 100 cloud to ground lightning strikes somewhere on the earth. Most lightning strikes average 2 to 3 miles long, and they carry typically 10,000 to 20,000 amps. Okay, that's the current flow. Now the 100 million volt term, that's a little iffy. because that's dependent upon the dielectric strength of the atmosphere, how high it is above the atmosphere. And that is the potential prior to the strike. So saying there's so many volts in a lightning strike is, that's just prior to. It'd be considered like an open circuit voltage, where there's no load on it. And then when the discharge occurs, it's like a short circuit current, or it is a short circuit current. So you're basically short circuiting that little circuit that's involved in. Okay, you do have a positive or a positive giant lightning strike that can hit the ground up to 20 miles away from a thunderstorm. I'm not going into how a thunderstorm generates the lightning and all, but suffice it to say, it's drawing charge from the whole area around it, and it can be up to 20 miles away. And you can get positive, when you get negative charge pulled into the cloud, you get the opposite stripped off, positive electron elsewhere, further out away, as much as 20 miles out. And the opposite charge, you have positive up in the atmosphere, the opposite negative would be in the ground, where at the other area, it would be the opposite charge there. If the positive charge breaks down, then these are quite often called bolts from the blue. They strike between the storm's anvil and the earth, and it can carry several times the destructive power of an regular strike because of the wind buildup and all this. Thunder can be heard about 12 miles away under good, quiet outdoor conditions. Temperature of a typical lightning strike is hotter than the surface of the sun. The odds of being struck, about 1 in 3,000 to 12,000. I'm getting different odds depending on who you reference, and depending on where the location is in the earth. If you got a drier atmosphere, then you're going to have a larger charge buildup between the 2 points, which means more energy, which means it'd be less likely to be struck. But if you did get struck, it would be more severe. Okay, how big around is a typical lightning bolt? We're talking about the main bright channel that I was showing you a few minutes ago. It's about the size of a quarter to a $50. And it looks much brighter than that because of the light and how bright it is. The lightning strike can create powerful radio frequency waves. Okay? As soon as it strikes, you're going to get static. And you can take your AM radio in your car, so you're driving around, and you think a thunderstorm, if you want to see if one's nearby, you can tune your AM radio to 770 kilohertz, and you can hear it crackle and pop, and hear the storm going on at that frequency. But it will create different effects in different frequency ranges. Like after 3 a.m. local time here, you can listen at 3 megahertz, and you can hear the dispersion ringing of the static as it bounces back and forth between the Earth and the ionosphere. And it can at times sound like hundreds of little tiny bells twinkling at once. What kind of damage is done? Well, insurance data found in State Farm there were about 115,000 likely claims in 2013. Down 24% to 2012. And it puts the average lightning claim was at $5,869. That's a little bit lower than it was in 2012. And this is the latest statistics I can find. And they also said that lightning strike costs the insurance industry as much as $790 million in the year 2015. Now, what we're looking at here is the probability of the intensity of a lightning strike. Okay? So what this is saying, what this little chart here is saying, is that 50% of the strikes are at least 30,000 amps or less. Okay? So if you have a strike nearby your house, or if it happens to attach to your house or your car or anybody, it's going to probably be less than 30,000 amps. Now, if you're wondering, aircraft in the aircraft industry, they design to survive a 200,000 amp direct strike. Okay? So it's less than 1% of the lightning strikes that have been recorded to date have been greater than that. So it's a high probability that all your aircraft are flying still safe and will be for a long time. Okay. Has anyone here been struck by lightning? You have. You directly or your house?
Oh, my house.
Okay, I'm saying directly, person. You have?
I have not, but my uncle was, and he was in the hospital for a month, and he still has effects to this day.
Did he get the red rash? And
Pain in his nerves, couldn't see straight for a long time, still has trouble seeing.
Did he?
Still has ringing ears from it.
I'm sorry to hear that. Did he get the red rash and all that with it too?
He was
That's very
actually
rare.
an electric power company lineman, and he was hit while he was up a pole.
Oh,
So the line was deactivated, but the lightning hit him on the pole.
Yeah,
Because he was the tallest object around.
yep.
And this was in Wyoming where the atmosphere is very dry, so it's very severe.
I'm sorry to hear that. But I got another question too. How many people here have been shocked from electrostatic discharge? Okay. The basic physics behind that little electrostatic discharge is, basic concept is the exact same as a lightning strike. The only difference is the intensity. You build up a certain amount of charge on your body. You're approaching another object that has an opposite charge because it collects. And then as you get closer and closer, it discharges. The real severe ESD charges, you'll hear a zap and you can actually see the little arc. It's exactly like a lightning strike. So in a way, everybody here has been struck. Just very, very small. Okay, has anyone here had their house or communications struck? Okay. How many of you had damage? Okay.
I'm 100%.
All right, we're going to talk about the concepts of how to improve the probability of not having damage. There is no foolproof way to 100% guarantee you won't have damage. All you can do is ask Mother Nature to go where you want it to. And I said ask, because you can't force it to do anything. Okay? Another question, does lightning strike in the same place twice?
Yes.
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 Okay, yes. If it didn't, lightning rods wouldn't work, would they? Does lightning strike from the cloud down or from the ground up? Answer's both. Answer's yes, it does, both. Okay? Now, what's happening is, let's go back. When I say that it strikes from the ground, or cloud down and ground up, in the first picture I told you about those little leaders, those little light streaks that never did finish a connection. And then you have your main channel. Well, just prior to the formation of that main channel, as the two charges in the atmosphere and in the ground become more intense, they start stressing the material, the atmosphere in between. Now, what's going on there is called leader formation. Now, these leaders can jump 50 feet at a time. Okay? So you get this matrix of leaders coming down, and you get a matrix of leaders coming up. And the first two to connect, as soon as that connects, all the energy in those leaders dump into that channel. Okay? And as it's dumping into the channel, the channel expands, gets hotter, wider, and more current flows through it. That's where you get your waveform. So when you see the picture where you get the flash and you see all the leaders, what you're seeing is that the leaders, all the energy is, the electrons are flowing from the leaders into the main channel. And the main channel is neutralizing the potential between the 2 points at either end. So it's a race. And that's why it's not always predictable exactly where it's attached, because the leader formation, given all your heads are at roughly the same height, if the leader formation was come down, you'd be drawing leaders off of every one of them. Now some of you be more than others, depending on how conductive your skin is. Because of what the moisture content, ions, and things like that. So, some rough costs of what it takes to protect your equipment and house. Roughly about $2,000 to $5,000 for direct attachment. Input power coming into the house, $2,500 to $1,000. Primary phone, $50 to $150. Satellite, up to $200. Secondary protection. Now, what I mean by secondary protection, you know all these little power strips that you go by? Okay? And they say have surge suppression and all of them. They are not designed as primary protection. If you do not have the input power to your house protected, those will blow up. Because the first line of defense for any of the threats coming into your power distribution system of your house from the power wires is the entry panel to your house. If you don't have any protection there, then you're asking a unit to handle a lot more energy than it was designed to in the first place. Okay? So without one, the other one doesn't work. And what we're going to get into in a little bit, to give you a hint here, is none of this works if the grounding system's not good. You don't have a good foundation. Because without that foundation, you don't have a good path for that neutralization of the two potentials to travel, that current to travel in the path you're after. Okay. There are 4 basic causes of damage to your electronics, to your radios, to your TVs, to your VCRs, to your phones. That's direct attachment. It's when the channel directly attaches to your chimney, to your power lines, or to your house even. The lightning channel, the indirect, is a field coupling. Let's say a lightning strikes the ground nearby. Anytime you have current flow, you create an electric field and a magnetic field. Okay? Anytime you have wires or cable harnesses of that nearby, or loop areas, which we'll get into a little bit, you're going to get energy coupling into that adjacent wiring, those adjacent circuits. That's called indirect. And then you have power surges, which happens to power company, where you have a lightning strike a few miles away, take out a transformer, everything shuts down, tries to come back, you get a surge when that occurs. And power transients in general can be caused by lightning strikes. So, there are 4 stages. As I said to begin with, your grounding and bonding is going to be your most critical. Your second is going to be physical protection. Now, the physical protection is typically lightning rods or tall objects adjacent to your house have a higher probability of attachment than your house. But the problem there is, we're going to get into, is you either have a tower, radio tower, or a tree that you put your you put your antenna into. That usually puts that element, a metallic element, higher than your house. So it increases the probability of direct attachment to those locations rather than your house. The third one is your primary equipment input to your house, and the last one is that secondary protection. there any questions, comments? Okay. Yes, sir.
I don't all houses that lighting houses. But I know up in Virginia, some of them have lighting. Why don't we have that here?
Well, because the laws don't require every house to have that, and it's left up to, it's a personal decision as to do it. If you've noticed the government buildings here, all of them have lightning rods, direct attachment protection. Now, I'm not saying everybody here has to go out and put direct attachment protection on your house, put lightning rods on your house. You don't have to do that. You can if you want, and if you do, it will protect your house better than it is today. But because we have such high trees and all, and we are such dense trees and everything around and higher objects around you, then the probability of attachment to your house is less. Now, if you're in an open pasture and the land's all flat and the highest point is your house, then you probably need some direct attachment.
The secondary housing, which you talked about in the previous slide, which field is worse, the E field or the H field?
Depends on the wire terminations. That's a couple. I'll talk about it in just a few minutes. Okay, the grounding scheme to the earth is going to be the foundation of your protection system. Because the charge potential manifests itself in the earth, one half of this charge and the other half is in the atmosphere, those electrons are going to be pulling from the earth. Let's, just for an example, let's say it's negative charge up in the atmosphere and it's positive charge collecting underneath. The potential of the metal, the wiring in your house, let's say green wire safety ground, is basically going to effectively raise this point here, which you call Earth, because this is metallic here, it's going to raise it up to that level. Because the electrons can flow very freely through metal. Okay? So if the positive charges are collecting here, it's going to draw and try to draw the negative charges here to first try to neutralize it, right? That'll be the quickest. Well, as soon as it does that, then this positive charge potential relative to the atmosphere is going to be at this point up here physically, not down here. That's why you're going to have leader formation coming off of these things. Yes, sir?
When you're saying positive charge, you mean absence of electrons.
Correct.
So electrons are restricted on the outside.
Okay, got a couple of questions for y'all before we get into. I'm going to step through a simple model of what's going on during the lightning strike for you to explain why a grounding system works and what it's actually doing. So first question I have for you right now is, what's your grounding approach? What's your protection approach for lightning?
Really good home.
Disconnect the antenna. Okay, so you disconnect it outside or inside the house? Inside the house, okay. So you brought the cable wire. So you've got this first typical installation, right? Got an antenna up there. Say, oh great, I've got a bedroom in the back here. I say, I'm gonna set my radio up there. I've got my antenna up here. I'm just gonna bring that coax down, bring it in through that window, put it on that table bench. Now that radio is connected to the power through here, and then there's your ground reference, right? Your earth reference. That's your typical one. So that brings that charge all the way up. Now if I disconnect it and lay it over to the side, about what's the distance from the end of your connector to any local metal object? A foot, okay? Remember I told you a little earlier that a leader formation was 50 feet? Okay, what's that foot doing for you? Not enough.
Throw it out the window.
Needs 49 more.
Needs 49 more. Well, a friend of mine was sound asleep one night, and he woke up to this very loud sound. Startled him. He jumped up and went running around the house, and he smelled electronics, the smell of electronics burning. And he does exactly the same thing he did the exact same thing you just mentioned. And he had about a foot away. And the arc, the lightning strike that came down through his antenna, through the shield of his cable, to the end of the connector, had jumped to multiple electronics. He even had one piece of electronics that was a piece of test equipment that wasn't connected to the, it was battery powered. It wasn't connected to the power of the house, but it happened to be in between two others, which it used as a stepping stone to get across. It even melted some of the bolt heads on his rack that he had. It had enough strike. I usually have pictures of all that in my slides, but I thought it would take too long to go through that. So the issue is, that's not going to work. It helps. It helps decrease the probability of attachment damage, but it doesn't really work.
So after you disconnect it, you throw it out the window.
That's a better option. Yes, ma'am.
I've heard of people who put them in glass jars or jars full of marbles.
Yeah. All that's doing is trying to increase the dielectric, which means, in simple terms, they're trying to make it appear to be further away.
Does it work?
It depends on.
How many marbles?
Yes. It depends on how many marbles. It depends on the contamination. Yeah, you've lost it. It also depends on the contamination on the surface of the marble. Okay? An insulator is only as good as the surface it has. If you've got dirt and debris in those marbles, then they're going to have a little more conductivity than the glass marble itself. Now, it will help. It will lower it. It'll be better than just throwing it on the table. But it's still not a solid solution. Now, if you disconnected it and threw it out the window, and it was laying on the ground out there, that would be better. Because what we're going to talk about is how do you ask the lightning currents to stay outside of your house, outside of your communication shack. Same way an aircraft is built that says, how do you keep the currents on the outside surface to minimize the amount of threat on the stuff inside? I believe you raised your hand first. Yes, sir.
We're talking about that. We're talking about taking the connector on the end of the cable and doing something with it. Is that the only place the lightning would emit from, is the connector on the end, or could it come from the run of the cable itself, the shield cable?
We'll talk about all this in just a few minutes. Yes, sir?
Yeah, actually, I was wondering if you took like these 12-foot grounding that you pound into the ground, if you took a cable from that and you unplug it from a radio and fashion that to it, give it a path.
We'll talk about that.
Would that help? Okay.
Slightly ahead of me.
All right.
Just slightly. Okay, so the situation is what we just said. Just installed it. Lightning storm's coming up. I disconnect it. I throw it on the table next to it. Or I don't. I just leave it connected. Let's say I just leave it connected. Worst case. Now, this model is a very simple model, just to show you the concepts and show you the potentials of the threat. Okay. I'm not taking into account a lot of the parasitic effects. I'm not taking into account to inductance and things of that nature. I'm just taking resistance. Okay, the DC resistance of the metal in the antenna in the shield of the cable that's coming. Picture this as your elements of your antenna. This resistor represents all the shielding cable harnesses up to your radio. Say your radio is right in here. That shield is connected to the green wire safety ground inside your house. And this resistance is the DC resistance of the cable shield going through the house. And this resistance is the resistance of the ground rod to the earth. Okay? And you notice that it's 25 ohms. Where did I get that? Huh? Yes. Correct. Correct. Close enough, because it is a very low frequency that they take the measurement doing the ground potential drop-off test. So I'm using the 25 ohms. NEC code says 25 ohms. Now, where did that 25 ohms come from? What's the NEC concerned about?
Safety ground.
For humans, right? They want to make sure that you don't get hurt if the internal wiring shorts to the ground wire, or you lose your insulation inside a piece of equipment or appliance, and it can shunt the energy away from you to this point so that you don't get hurt. The idea is to try to keep less than 5 milliamps going through your heart, causing cardiac arrest. Now, I can tell you right now, the NEC code is not interested in lightning. Lightning has a lot higher currents. So your house probably has a impedance closer, worst case, well actually it can be worse than this, because a lot of the residential installations, no measurements are made. They follow the code, they take an 8-foot rod, they pound it into the ground. It's typically a 1/2-inch rod, and that's it. They meet code, done. Yes?
They have to do 2 rods now if they don't measure. You have to do 2 rods now if you don't measure.
Okay, 2 rods now if you don't measure.
Yeah.
Look into that.
Where's
The code
that?
says
Is that when that code?
That's just the latest national electrical code.
Okay, so they just recently updated, and I'm not up to date on that. So let's say it is 2 rods. We'll get into what that does for you in just a few minutes. Now, if you assume 10,000 amps attaches here, that's going to flow through here. Now, air will break down at about 3 megavolts per meter. A meter is about that long. Okay? So 1 million volts for about 1.5 feet. Okay? So, in this model, simple model, this point at your radio would see 255,000 volts. That means it could jump about 3 inches. Okay, so I've disconnected it, or I've got this strike, got this current flowing through. Anything within 3 inches, you can cause an arc potential. You can potentially have an arc over to some other piece of equipment. Yes, sir.
225 kilovolts comes from 10,000 amps times 25 ohms.
Close enough, because these two numbers are very low. It's actually the voltage drop from here to here relative from here to here. So, yes, because that is such a low resistance there, it's roughly what you just said. Now, let's start with the ground rod.
Are you going to explain air gap and how that works?
Explain the
Air gap, what the concept of it and how it works? It
This-
looked like you had a set.
Okay, if you were to do the air gap?
Yeah.
Okay. Well, what that would do is if all the leaders did attach, and let's say you took it, disassembled it, and you laid the cable in the back, and just laid it on the table. Let's say the lightning strike does attach to your antenna, okay? The circuit is not closed yet, right? So let's use that, what was that, a million volts that we said earlier, prior to the strike? That would make, in this thought process we're doing, that would make that gap have 1 million volts across it. Okay? So basically, it reduces, it puts that, all that potential prior to the strike across that gap. Like I said, we're talking concepts here, okay? So you're gonna have a much higher than the 255,000 volts across that gap. And it can jump as much as 50 feet. Did that answer your question?
I was actually thinking of some device I thought I had seen that basically looked like it had a gap in it.
Oh, you're talking about arc gap protection?
Yes.
Ah, now that's different. All right, what an arc gap protection is basically a device that has very two sharp points that are set at a specific distance between them, that has a gas inside that area, such that it will break down at a certain voltage and shunt or direct the current away from everything downstream from that.
Okay, yeah.
That's how that works. You still get the same potential and all, you get it built up, it'll build up to where that breakdown point is, and then it'll discharge through there.
Ideally, that being the path instead of where.
Exactly. The idea is directing the currents away from anything going inside. So the arc gap, that's how arc gap protection works.
Is it destroyed when that happens?
With a typical strike, no. But each time it is struck, it does have a little bit of molten metal, a little bit of melting at the tips. So as the device is activated more and more, those tips melt, therefore the gap gets wider, therefore the voltage breakdown point gets greater. So they have a finite life with it. Now the arc gaps can handle a lot more current than your your MOVs or your Zeners and other surge suppression devices, but their breakdown point is not as stable, and their lifetime of maintaining that break point is not as stable. But they do handle much more energy. Okay. Here's how ground rods are supposed to be installed. There it is. Okay. It's supposed to be where this joint is buried and underneath the cross line. And this is your ground conductor coming to it. Okay. And we'll get into bin radiuses and some of that stuff here in a few minutes. Okay? It's supposed to be 8 feet in the ground. It's supposed to be a total of 10 feet, so it's supposed to be about 2 feet underneath the surface. They don't do that here. They leave the top end open and they make the bond outside, make the bond up in this area. That allows the environment to get to it, that allows it to grow, that allows it to degrade. And you can't inspect it when it's under the ground. So kind of a trade-off there as to how they want to maintain the standards, inspect it, and guarantee it versus what works.
I had you're gonna hate this guy too, but I had a cable guy come and he was testing the line and things like that.
Yes.
And he felt it necessary to disconnect the ground for his machine to work, for his device to get his good signal, and then he hand tightened it back. Bring your neck.
That's not a good application, no. That can cause more problems.
You can lay your ground rod horizontally.
Yes. The way the ground rod gets its impedance relative to the earth, the way it manages that is by surface area. Okay? The surface area of the rod itself, not the thickness, but how much surface is in physical contact with the earth. So three-quarter inch rod diameter is going to have more surface area than a half-inch diameter. It's not going to be significantly more, but it is going to be more. So the impedance between the rod surface and the earth is going to be slightly lower with that. And then you have to deal with the conductivity of the earth itself that's making contact with the rod. So we can talk about that a little
Based
bit.
on what he was saying, you could literally put your rod in horizontally then?
Yeah, you can, but the idea is you'd have to have it below the frost line
Okay.
to do that. And it's the impedance of the rod to the earth is what I was getting at. I guess I didn't make it clear. Is that if you put it in horizontally, it's going to be the same impedance as if you put it in vertically, as long as the conductivity of the earth is the same in that area that's making contact. You want a physical contact here. You don't want the bend radius to be greater than 8 inches. I mean, less than 8 inches, Because what's happening here is the lightning current flows through this bend. You're going to get magnetic fields around it. And those magnetic fields are going to be such that it's going to try to straighten that wire out. Okay? If you have current in 2 wires that's opposite, it's going to try to pull those 2 wires together. When you have current flowing in one direction, a single wire in the bend, it's going to try to, they're in the same direction and they're going to try to force each other apart. So it's going to try to straighten out that curve. Okay? So you'll see guys that bring the green wire safety ground, it'll come down, go into your ground rod, and it'll be a real sharp bend curve right there at the ground rod. If a direct strike occurs, there's a good chance that the physical or mechanical strength of that joint will be broken.
Is that for all size conductors?
Excuse me?
Is that all for all size conductors?
No. As far as the idea of it trying to straighten out, yes. As far as the mechanical strength of it, it depends on how strong you put it in. The fields are generated by the total current going through the wire. You're asking about the current density on the wire. It's going to be less and the current density is going to be less in a larger wire, but the field strength should be the same. Now you'll see lightning cables that are used for your direct attachment. Some of them will be a large stranded, like this. Some of them will be a weave. Okay? The weave is actually a better lightning conductor. The idea behind the stranded and the weave is to increase the surface area. The weave is such that they try to weave it to minimize the amount of inductance, but it also increases the surface area, because if you've got 24 strands of 22 or 24 strands of 18 gauge wire, or 24 strands of 20 gauge wire that's woven, it's got some airspace in there, then you're going to have more surface area. And what's actually happening there too is when the lightning strike's occurring, the lightning channel and the arcing that would go on inside that cable would actually make a plasma type situation where it can carry more current without damage, and it'd be a higher surface area. So and it'd be less inductance in it, so you'd have less of a voltage drop potential between 2 points. So the weave is better than the stranded. Is the coiled. The coiled is better than a single solid wire, and we'll get into some of the impedances of those wires and all that.
You don't like ground?
Excuse me?
You don't like copper ground?
We'll get to that.
Inductance is not our friend.
Correct. Inductance is not your friend. Okay. We just got struck. We just got damaged. We just had to buy new equipment. What's the next step? I heard if I put a ground rod in the ground, and I put a metal copper plate right there as the cable comes in, and I put a surge suppressor, arc gap, at this point, I'll be happy, right? All right, I've got a no over here. You're correct. So let's look at that one. What we basically have done is we put a 25 ohm impedance at this point where the cable comes down and enters the house. Now that's better than it was, because now we lowered our threat by half to 127K, right? But part of the problem is this impedance is high enough, and that's so much current, and this impedance is low enough, that the actual current's gonna go through your house still. It's gonna go through the green wire safety ground in your house. Yes? Oh, okay, got that too. Okay? So yeah, it'll drain off a little bit, but that's too high of an impedance, and you're only gonna cut it in, if you're lucky, the voltage potential by half, so you'll split the current by half. The current will be lower, but it's not gonna be ideal. So what do? You need to connect a copper wire from this ground rod to this ground rod, and you need to improve the impedance of that ground rod to the earth, because you're trying to make the path from this earth to this point here lower so that the current doesn't go through your house or go through your communication shaft. Okay, so how do we do that? Well, one, this piece of wire has to be bare, it needs to be bare copper, and it needs to be buried below the frost line. Okay? Yeah. Here, I'm giving you ideals, guys, so that you understand the concepts. And if you want to talk to a professional as far as an installer and all, you can go talk to him intelligently and make sure he's doing it right for you. Okay? Yes, sir.
I've got number 6 doing between around but it's 4 years I can't really see it underground.
Right.
I'm in Georgia, I'm not worried about freezing, but can I still walk up on freezing?
Well, luckily you're in Georgia, so the only time you're really at risk there is when the frost does get that low. It's about a foot in Georgia during the worst part of the winter. So 90% of the time, no, you're fine. It's
Better than zero.
Yeah, it's all percentages. Like I said, we're trying to lower the risk and ask the Mother Nature to go where we want to. Yes, sir.
On number 6 wire, I read a long time ago, the number 14 wire was higher than any lane.
Depends on how long it is.
That should be like the second one, when you can fly.
The wire itself?
The false width.
Oh, the pulse width, yes. Pulse width is, yes,
50% 25.
70 microseconds, roughly 70 microseconds is the pulse width. So you can calculate the inductance.
A lot of current, but it doesn't last.
Correct, correct. So as far as melting and all, yes, it could probably handle it. It does handle it with no problem, 14 gauge wire. However, the voltage potential across it is going to be higher than is if you use 6 gauge. Plus, he's got bare number 6, bare copper number 6 buried. So the surface area that's in his number 6 is going to be greater than the surface area in 14. So the impedance is going to be low.
That's what I'm saying, it's a place where it's back there, so it's all above ground.
It's above ground? You can't lay it on the ground?
Well, probably go several states in the center and rise some.
Well, let's talk about that. Okay? We'll hopefully get to that. Okay. So, first question. How do we lower the impedance of the ground rod? What happens when we put 2 in? If you put 2 in very close to each other, say within 3 feet, then nothing. Very little. It doesn't help the impedance significantly. Now, if you put the second ground rod in a distance equal to the height of the ground rod. In other words, if you got an 8-foot ground rod and you put your second one 8 feet out, then you bury the wire between them, then your impedance would go in half. So you'd be going from 25 ohms down to 12. Okay? But in order to protect for lightning, the typical number you try to reach is below 5 ohms. Okay, so we're talking a factor of 5. So how can you do that? Here's an arrangement where they're 60 degrees apart, they're 16 feet out, 8 feet down. with the soil, assuming a soil resistance of 62 ohm meters, this will give you 5 ohms. This here will give you a third of 25, or about 8 ohms. This will give you approximately about 10 ohms, I'm sorry, about 10 ohms. This will give you about 5 ohms, this arrangement. This here will definitely be less than 5 ohms if you go the whole perimeter of your Radio Shack or your house. People around here, we can't do. And then your NEC code.
Greg, what's the typical resistance in Georgia, would you say? Is it
Between 20 and 25 ohms because of the clay. Yes, sir.
I saw a thing one time, power guy comes out and checks the, owns the grounding rod.
Yes.
And what he did, it wasn't enough, so what he did, he put a couple on it. He took another ground rod on top of that, and just kept on driving until he got it to where he wanted it.
Yes. He was increasing the surface area
Yeah.
to try to lower that impedance. And that's really what you're doing here.
Set the space them out instead of trying to drive on top of the other.
Correct, because it's hard to get that deep around here.
Yeah.
Now, if you're in Florida where it's sandy, they drive them really deep.
Yeah.
Okay. Now, yes, sir.
All that labor is being done by factor 5.
Yeah. That's a personal choice here again. What do you think?
Factor 50 to 500. Then I'd be interested.
Yeah, well, you're gonna get, the way it works is, if I have one rod and I put 2, I cut it in half. In order to get it half again, I have to put 2 more in. Okay? So there becomes a point of diminishing returns. And that point has to be decided by you. Now, there is another technique that's called a Ufer ground, and I'll describe that in just a second. But what I want to point out is, under lightning conditions, the surge impedance. Now, this is starting to take into account the inductance of the rod, the ionization of the earth around it, and as I said before, all the analysis I'm showing you is a simplified model. But just as a reference point, when that surge is occurring, that impedance can be as much as 10 times what we started. So if I started with 25 ohms NEC code and I have a granddaddy strike, that surge impedance would be 250. What does that do to those voltages and potentials inside your house?
10 times higher.
Yep. So the idea is trying to keep currents outside your house. Try to make your grounding system structure stable. Try to make the points look the same equal potential through there and have a large surface area. These are the concepts that we're talking about.
You're scaring me.
Oh, sorry. That's life. Not doing it on purpose. But there is hope. There is hope. If we were to take those 2 ground rods, bring them down to 5, and bring the wire in between, now we're down to 25 kilovolts, which is only approximately a third of an inch. Okay, if you wanted added protection over that third of an inch, disconnect it. Make sure it's in a glass jar and all that to try and get your probabilities down. Yes, sir.
I've got twin link, couple twin window,
Yeah.
board, and got the door 23. What I've been doing, and then I've got my common point, one through 2 old Illinois 40-200s, each side of the house in the ground rods. And what I do is just tie those to the ground instead of letting it loose.
Mm-hmm.
It's inside, it's still close, but.
Yeah.
Am I improving anything?
You're improving it, but you're running the risk of bringing those currents and all inside your house. And when you penetrate your house, the wooden structure and all, if those wires going through or close to any metals and stuff, any insulation, it's just it's not as well as it could be if you've done it outside. Plus, the question is, those ground rods at that point, and all, are they tied to the main ground rod coming into your power distribution system?
Yeah.
Okay, good. That's a key point. Because if you don't do that, if you don't put that wire in the ground underneath between the 2, yeah, it'll lower it, but it still lets the current go through the house itself. More current go through the house itself.
And that obviously goes at that same point, this is a common point. That's going through, a ground
Yeah.
link,
Mhm.
all my equipment's tied to that, so it's all together, that's,
Well, it all being to that, all being together like that, that'll all raise at the same potential at the same time, so you won't get arcing in between those. But anything that's close by that isn't tied to that, you'll get a voltage potential across there, and that's where your arc comes. If you jump over to the other parts of your house.
I got a question.
Yes,
Could you explain what step fault voltage is?
a step fault?
Like the drawing you have there, there's something like called step fault voltage between the two ground rods?
I believe you're talking, I haven't heard that term, I'll be honest with you, I haven't heard that term. But I'm assuming that it is a hard fault that causes an impulse such that the inductance of this wire would cause a voltage potential between those two ground points. It's what it sounds like you're describing. But I'll be honest, I'm not familiar with that term. Okay, get to 614. Typical recommended. Now, I'm taking this from the telecommunications industry, which builds the communications stacks, communications buildings at the bottom of all the towers for the cell phones and other communications equipment of that nature. Motorola has a standard out there. I think it's got its reference here. 56 is the number. If you're going to go, if you got a distance less than 13 feet, number 6 is good to use. 14 to 20, number 4. You notice as you get longer, they get higher gauge. That increases the surface area and lowers the inductance. Okay. Nowhere on here is 14. Just because it can handle the currents without melting doesn't mean it won't cause other problems. Now, talking about inductance, just to give you a little bit of idea, 12 gauge wire, the DC resistance is a 132 micro, that's 10 to the minus 6 ohms per inch. Very low. Okay? But at the 2 meter band, here, 2 meter band, that same looks like 2K. Now your lightning strike is going to be below, the energy content of the lightning strike is going to be in the kilohertz range, okay, hundreds of kilohertz, not up in the megs. So if you use the 2 meg for lightning, a 12 gauge wire is going to look like 27 ohms, not micro ohms per inch. So if you're looking at a, let's see, what did I say here, a 60-inch cable, 5 foot piece of wire. Okay, if I'm looking at a 5 foot piece of wire, the inductance is 2.2 microhenries, and at 2 meg it's going to look like 27 ohms. 1 opt is going to look like 22 ohms. You notice there's not 5 ohms difference here. You go to the rope weave, 17 gauge, 30 strands woven, that's fine. Now if you go to the braided straps, that's doing better. Okay? Yes, sir.
I know that the inductor goes down very slow.
Yes.
It's just, inductor goes down, what is it, hovering?
What, the inductance? Natural log of L over B. Yes. It's the diameter that's the, yes. It goes down slowly, but natural log is a reference to the diameter. Okay, now number 4. We've added another ground rod at the bottom of the cable harness where it comes down either your tower or your tree, and I'm missing a wire that goes between these two. I need to update my drawing. Okay, so that means that the majority of the current surge will come here, what residual will come here, and flow into here, and very little would go through your house. We did that. Now we've got our gap down to 0.2 inches. So these are just to give you rough numbers, rough ideas, and the main thing I want you to walk away with is the concept of what you're trying to achieve here, what you're trying to do. One of the products that are out there is this mounting bus bar. This was normally found outside the facility, right where the cable harnesses are coming into the facility. This is where you would mount your arc gap, where you mount your surge suppression, and all to try to divert the energy from coming in on the center conductor. Because as the current is flowing in the shield, it is inducing a current in the inner conductor as well, and you're getting a voltage potential between those 2 points, and that's what can damage your radio as well. Okay. Coming down at the bottom of the tree or bottom of the tower, you've got your ground ring around the base of the tower. It is Motorola 56 standard, if this is an example from there. You've got this bonding for the shields to be terminated at the tower base, and then these cable transmission lines go out to your building. So, from the communications industry, I kind of just said we got a monopole or a Yagi or something like that for the ham radio operators. You notice all the joints need to be bonded together in the tower. If you have a joint and you don't think it's a very good one, then you need to put a mechanical bond strap across one of the legs across the joint, and you're putting multiple sections together. Bring that down, and you have a ground ring buried with a minimum of 4 ground rods around the tower. If it's a small tower, you can get away with 1 or 2. Excuse me. You bring that, bond it to here, you have the ground rod, you have the ring around your communication shack, and then everything going into the communication shack should come into 1 point, okay? So that you're not setting up a path inside the building to go from here to here. One of the things I want to point out that'll help you the most is you notice we're trying to make this point here because we're coming in at some place way on the other side of our house, which is typically not the same or close location to our power entry point. We're trying to make this point look at the same potential as this point. If all of this came in right here, you could get away with not having this rod, but just have your multiple rods put in and have that as your one reference point. And then the potentials inside the house would not be that great.
Question.
Yes.
How long a distance would you say that situation would apply where your service mains are as close to your entry to your shack? 10 feet, 5 feet, 20 feet?
I'd say if they're within 15 feet of each other, and if it was me, if they were 15 to 16 feet apart, I would just run the wire in between 2 ground rods, and you'd be done. Okay? If you start getting less than that 16 feet, then the only thing I would do is increase your number of ground rods at that point. Okay? All right. How do you choose your surge suppression? All your surge suppression has 3 parameters that they use to characterize them. The clamping voltage, the current that it can handle, and its energy rating. Which of these parameters is the most important? Joules. The energy rating, correct. How many joules can it handle? Because that's giving you an indication, depending on the time duration of the thread. If it's 70 microseconds, 120 microseconds, 50 microseconds, that actually determines the clamping voltage and the amount of current it can handle. Because the device is a joule thing. It has to dissipate this energy as heat. So it has to be able to absorb that much energy and convert the heat to dissipate that. So Yeah, these points are given to you relative to a standard of what's called a 10 by 1,000 waveform, which is a 10 microsecond rise time and 1,000 microseconds to 50% decay. But first off, you want to pick that. If you're going into this, you pick your highest energy rating. Then you need to make sure you're meeting your clamping voltage. And those two things there will set your current for that test. This is not a plug for any particular device or company. These are just some of the surge suppressions for the whole house. Excuse me. Whole house that you have coming in that Cutler Hammer offers. You can get an electrician to install these. You can buy this or have the electrician buy it for you, have him install it. Costs you about $150 for the part, and they'll probably charge you about $100 to install it. The other option is Georgia Power. If you have Georgia Power, they will come and install it, and they'll install their device and all. They'll give you some type of insurance with it. Cutler Hammer will give you insurance as well with it for damage to anything inside the house. But the Georgia Power one, they'll charge you, I forget how much it is now. I think it's around between $5 and $10 a month forever.
Yeah, that was, now you're on.
Yeah. Well, that's just
The flip side of that is if it takes care of the deductible.
correct.
It's
Correct.
worth it, so
Yeah, it's all how you look at it. Okay, I'm about done. It's surge suppression, yes, sir.
What about these induced damages, which is uniquely on the HG?
This will help protect against that for any of the coupling for a nearby strike that would be induced in the power cables, and that energy would be coming in through the power cables. That's what this is for. And this is just an example of a arc gap. I've run out of time now, so I'm not going to go into the details here. And here's some references if you're interested in researching it a little bit more. Some industry standards. And this is where my experience in working with these standards and to these requirements, and just where it's coming from, where it's all coming from. Yes, sir.
I see page numbers. What book did this come from?
Excuse me?
I keep seeing page numbers. Is this a publication that's available?
No, this is just me. That's how many slides I have. That way I can judge how long this is going to take. Just find out.
Do
Yes,
you have a
sir.
YouTube video up anywhere?
No, I don't, but Ours is kind enough to film this one, and they said they're going to put this up on their website, their YouTube. But you said it's
GarsTube, GARSTUBE. It's YouTube/GarsTube.
okay. So the answer is yes. It will be good. Thank you.
Thank you.